Waves and light. So electromagnetic waves carry vibrations in electrical and magnetic fields. So kind of like the way the ocean carries waves, electrical and magnetic fields carry magnetic waves. So the entire wave can be thought of extending infinitely in both directions. The wavelength is going to be the distance between two consecutive peaks or troughs on the wave. The frequency of a wave is defined as the number of wavelengths per second that travel past a given point. So take a moment to pause this video and answer this first question. So there's a couple different ways, several different ways that we could draw a wavelength here. So you can go from a crest to a crest, you could go from a trough to a trough, or just from one point to the next identical point on the same wave. Here, we could have a wavelength. Here we have a wavelength, trough to trough, or even here to here we can have a wavelength. So if both waves here are traveling at the same speed, which one has a greater frequency? So if these waves are traveling at the same speed, the one with the shorter wavelength is going to have a higher frequency because there's less distance in between waves. Each wavelength is shorter, so more of them can go by per second. So for a wave traveling at a given velocity, how does frequency depend on wavelength? So the shorter the wavelength becomes, the higher frequency the wave will be. So longer wavelength means lower frequency, and shorter wavelength means higher frequency. So based on the information on the table here, I want you to go ahead and take a moment to fill in these blanks. You can pause the video and then return here when you're ready. So looking at the table here, first we want to compare what happens with frequency and energy. So if we look in the table here, when the frequency is a big number, my energy is a big number. So as the frequency of a wave increases, the energy will also increase. As the wavelength increases, so now we want to compare what happens with wavelength and energy. So here we see that as my wavelength is getting longer, my energy is getting smaller. So as the wavelength of a wave increases, the energy will also decrease. Okay, so radiation is energy that travels in the form of waves and makes up the electromagnetic spectrum. So radiation within the electromagnetic spectrum is divided up into two major categories: ionizing radiation and non-ionizing radiation. So I want you to place the following sources of radiation on the electromagnetic spectrum where you think they belong. Some types of radiation may have more than one source. So here's how I filled mine out. So I looked at the FCC, the Federal Communications Commission, and so it made sense to me that things like cell phones and communications tower, radio towers would be regulated by them. So I placed those with radio waves. Next, we have microwave and we have microwave oven. So the way this works, you put your food in the microwave and it bombards it with microwave radiation, which causes the water molecules in the food to spin, which makes your food warm up. The microwave oven was actually kind of conceived whenever a scientist who was working with microwaves noticed that the chocolate bar in his front shirt pocket had melted after he had been working with microwaves. Next up, I put infrared with remote control. Computer screen, I think a little bit infrared and a little bit of visible. Like if you hold your hand near it, you can feel a little bit of warmth. And then with visible light, I put light bulb. I also put cell phone because most cell phones, we use light to see to use them. And then tanning bed, I put with ultraviolet. So tanning bed is visible light and a bit of ultraviolet, which is why you want to be careful and avoid kind of exposure to tanning beds because ultraviolet rays can cause some problems for your skin. Next, under X-rays, I put X-ray. These are pretty high frequency ionizing radiation. So that's why we kind of want to limit your X-rays to just when you break a bone. So obviously if I am, I have a broken bone, that is a much bigger problem than this little bit of exposure I might get from an X-ray. And the X-ray can give doctors very useful information about how to set my bone and how to make a repair there. So gamma rays, that would be radioactive waste. It also makes sense to me that would be regulated by the U.S. Nuclear Regulatory Commission, as well as the EPA. Tanning beds, also regulated by FDA. That makes sense. It's a box full of light bulbs that you put yourself in. So you'd want that to be, as safe as possible. You certainly wouldn't want to be injured by it. And it makes sense that states would regulate that too. The person who's putting you in the box of light bulbs should know how long to leave the timer on. Okay, so the images and demonstrations are going to represent the effects of radiation when it is absorbed by atoms. So these white circles are representing atoms. So I want you to take a couple of minutes to complete this activity. So read the description for image A and image B, and then perform the two activities that are given there. Return here when you're ready to check your work. So image A and demonstration A, those represent non-ionizing radiation. So low-frequency sources of non-ionizing radiation are not known to present health risks. So your cell phone, radio towers, all that stuff, not known to present health risks. High-frequency sources of ionizing radiation, like the sun and ultraviolet radiation, can cause burns and tissue damage with overexposure. So you probably noticed when you rubbed your hands together that you felt the warmth from that friction. So image B is going to represent our ionizing radiation. So it can damage living tissue by changing cell structure and damaging DNA. So your DNA is made up of atoms, and when ionizing radiation strikes those atoms, it might knock some of those electrons out of that structure. And this can lead to errors when that cell goes to reproduce, and eventually those errors can lead to tumors and cancer. So we want to avoid exposure and take precautions. Now, there is a little bit of ionizing radiation that we experience from the sun, but that doesn't mean that you shouldn't go outside. It's still a risk versus benefit analysis. So going outside and being outside is good for you. It is healthy for you. And as long as you do things like stay in the shade and wear sunscreen, you're going to be protected from the worst of that radiation. Now, the way that I would label this is good vibes and bad vibes. But under X-rays, I would say okay-ish vibes because in small doses, they can be really useful medical diagnostic tools. Go ahead and pause the video and take a few minutes to work on these next 3 questions, and come back here when you're ready to check your work. So why are the color labels plural? So we have reds rather than red because red includes several wavelengths ranging from 625 to 740 nanometers. The speed of light is a constant, so it doesn't matter whether we're talking about red light or blue light or X-rays or gamma rays or radio waves. The speed limit is 3 times 10 to the 8 meters per second. So remember, this is a number in scientific notation. It's raised to the positive 8. So this is a pretty fast speed. So which color is the longest wavelengths and the shortest wavelengths? So the shortest are going to be your violets and your longest are going to be your reds. Now, once we step outside the visible range of the spectrum, we have ultraviolet on the high energy end. So that's what we call the wavelength shorter than violet. We call that ultraviolet. And those are going to be higher energy than our 452 to 523 nanometers. So go ahead and pause the video and take a moment to answer these 2 questions. And return here when you're ready to check your work. So which is more energetic, a red photon or a blue photon? So a blue photon has a shorter wavelength, which means it has a higher frequency. So it must be higher energy than a red photon. So remember that as frequency increases, energy increases. And as wavelength decreases, frequency will increase. So, transitively, we can say that shorter wavelength means higher energy. So write a sentence that describes the relationship between wavelength and energy. So as the wavelength of the photon increases, the energy of the photon decreases. We call this an inverse relationship. So waves are described by their velocity or speed, frequency, and wavelength. In a vacuum, empty space, all electromagnetic waves travel at 3 times 10 to the 8 meters per second. This is the speed of light, also abbreviated with a lowercase c. The frequency of a wave is represented by hertz, which has units of 1/second, so per second. So wavelength is measured in meters. So we're looking at a couple of equations here. First, we have v, velocity, equals f, frequency, times lambda there, which represents wavelength. That's a Greek symbol. We also know that v, which is the speed of light, is equal to 3 times 10 to the 8 meters per second. Light is a form of electromagnetic radiation made of photons. So each photon is has a specific amount of energy that is associated with it. So energy of a photon, E photon, is equal to h times f, which is frequency. So h here is just a constant, it's Planck's constant, and the value of that is given on the screen as 6.626 times 10 to the negative 34 joule seconds. So when you multiply this number, joule seconds, when you multiply that by a hertz, which is 1/second, seconds cancel and you end up with energy. Okay, so take a couple of minutes to digest that information and complete this table, filling in the blanks. So our first variable here is velocity, which is the same as speed. And this has units of meters per second. So another way to think of that is distance per time. How far did you travel, what distance, and how long did it take? F is frequency, which has units of 1/second, or you might also see s to the minus 1. So s to the minus 1 is just a different way of representing 1 divided by s. So those are both the same. Wavelength, which is measured in meters. Now, oftentimes, the wavelength will be given in nanometers, so we might have to do a conversion in order to handle that. So our constants, we have the speed of light. So that is 3.00 times 10 to the 8 meters per second. Planck's constant is that 6.626 times 10 to negative 4 joule seconds. So our constant here is in meters per second. So if our wavelength was in nanometers, I wouldn't cancel out and get the proper units. So I need to make sure that when I'm presented with nanometers, that I convert that into meters first. Okay, so go ahead and pause the video here and take a couple of minutes to work on this problem, and return here when you are ready to check your work. So first thing I need to do here is convert the nanometers, the 490 nanometers, into meters. So this is a good opportunity for us to practice dimensional analysis. So I want to convert nanometers to meters. And I can do that in just one step. I'm going to put nanometer on bottom and meter on top. This is one of the benefits of the metric system. So nanometer means 10 to the 9 smaller, so 10 to the negative 9. So 1 times 10 to the 9 nanometers is equal to 1 meter. So when we solve this, we get 4.90 times 10 to the negative 7 meters. So next we want to calculate the frequency of the light. So looking at the two available equations, we want to choose this one. Velocity equals frequency times wavelength. So we're looking at green light. We're looking at visible light here. So this means that the velocity is going to be equal to 3.0 times 10 to the 8 meters per second. We also know that the wavelength of this light is 4.90 times 10 to the minus 7 meters. See how we got meters per second and meters? And frequency is what we're solving for in this question. So V is equal to frequency times wavelength. That's saying 3.0 times 10 to the 8 meters per second is equal to what we're solving for, frequency, times 4.90 times 10 to the minus 7 meters. So in order to solve this, I'm going to need to divide both sides by this value. So it will cancel out here, and we're just left with frequency is equal to whatever this divides out to be. So typing this in your calculator, this is going to give you 6.12 times 10 to the 14. And the units on that, we have 1/second. Meters are going to cancel. So 1/second, or you could put s to the minus 1, or you could put hertz. In question 15, we want to know which is more energetic, a red or blue photon. So you've already answered this question, but you answered it qualitatively. Now we want to answer it quantitatively. So we know blue photon should be more energy than red photon. So to solve this, we're going to need to use those wave equations. So the first one that we have is that energy of a photon is equal to Planck's constant times frequency. We also know that velocity equals frequency times wavelength. So what I'm going to do is I'm going to rearrange this to solve for frequency. So I'm going to divide both sides by wavelength. And so frequency is equal to velocity over wavelength. Now I'm going to plug this guy into my equation here for F. So I'm going to get that energy is equal to h times velocity over wavelength. So this allows me to solve for energy all in one step. If you wanted to, you could use velocity and wavelength to solve for frequency, then plug that in and solve for energy. Mathematically, that's the same as doing it this way. So I'm going to start with that 700 nanometers. So my units for the speed of light and my units with Planck's constant here, all of those matter, and we know that we want to change nanometer into meter. So 1 meter is 1 times 10 to the 9 nanometers. So this is going to give me 7 times 10 to the negative 7. And I can do the same thing for my blue photon. So I'm going to put nanometer on bottom to cancel and meter on top. 1 meter is equal to 1 times 10 to the 9 nanometers. So this is going to give me 4 times 10 to the negative 7 meters. So now I just need to solve this equation twice here. So the first time I'm going to solve for my red photon. So I'm going to plug in my Planck's constant. So that would be the value of h. My speed, we're looking at visible light, so that's going to be 3 times 10 to the 8 meters per second. And we're going to divide that by my wavelength, which in this case is 7 times 10 to the negative 7. So when we solve here, the only unit that's not going to cancel out is joules. So we get 3 times 10 to the negative 19 joules. We can repeat this calculation for our blue photon. So 6.626 times 10 to the negative 34 joule seconds. That's the value of h. Speed of light is still 3 times 10 to the 8 meters per second. This time we're dealing with 4 times 10 to the negative 7 meters for our wavelength. So when we solve this one, we get 5 times 10 to the negative 19. So 5 is a bigger number than 3, so that blue photon is going to be higher energy than the red photon. Question 16. A photon has this frequency. What is its wavelength in nanometers? And what region of the electromagnetic spectrum would this be found in? So we're going to need to use both equations here. Or rather, we're just going to use this one, but then we're going to need to do a dimensional analysis conversion. So the velocity is equal to frequency times wavelength. So velocity is going to be 3.0 times 10 to the 8 meters per second, the speed of light. And frequency is 1.50 times 10 to the 14 hertz or per second. And we are solving for wavelength here. So if I have this equation, v equals f times wavelength, my velocity is 3 times 10 to the 8 meters per second. That is equal to 1.50 times 10 to the 14 per second, hertz, and times my wavelength here. Okay, so we're solving for wavelength. Probably do a little better than that. There we go. Solving for wavelength here. So I need to divide by 1.50 times 10 to the 14 hertz on both sides. So when I do that, I get that my wavelength here is equal to 2.0 times 10 to the negative 6 meters. So if I were to convert this into nanometers, 1 meter is 1 times 10 to the 9th nanometers. So this gives us something around 2,000 nanometers, which would be in the ultraviolet range. Last question, we have a photon with a wavelength of 1 times 10 to the negative 9. What is the energy and frequency of this photon? So we're going to be using two equations here. In order to solve for the energy and frequency. So go ahead and pause the video and take a moment to try this on your own and come back here when you're ready to check your work. So if I have velocity equal to frequency times wavelength, that means that velocity over wavelength will give me my frequency. So my velocity here is going to be 3 times 10 to the 8 meters per second. That's the speed of light. My wavelength is 1 times 10 to the negative 9 meters. So if I solve that, that will give me my frequency. So this gives me 3.0 times 10 to the 17 waves per second. So now I can plug that in to my energy equation here. So I've got Planck's constant times frequency, which we just solved for, so we're going to want to type this into our calculator here. And when we do, we get 1.98 times 10 to the negative 16 joules.